Hey guys, I hope you're ready for simultaneous multiple regression example because that is what this video covers. So we've walked through the overview of regression and we've talked about dummy coding. Now we're going to hop into doing a multiple linear regression, but a simultaneous one. So the simultaneous regression is throw everything at the wall and see what sticks. So we're going to use several predictors to understand one y variable. And you'll use all those predictors at once rather than steps. So we have a separate video for hierarchical regression to see how each variable changes. And the important part here is in italics while everything else is held constant. So each predictor is assessed as if the other variables are held constant or already controlled for. Some definitions to remember from our lecture video is little b, which is our coefficient. In R, this is going to be listed under estimate. And it's the unstandardized slope. So for every 1 point increase in x, you get b in point increases in y. And that's in the scale of the data that you're using. Beta, however, is standardized, and this is the z-score. And so with one predictor, beta is equal to r. But with more than one predictor, it is not. And these scores can go over 1 if you have more than one predictor. It's a common misconception. Since it's standardized, the use of it can be to compare across predictors to see which IV is the strongest. We're going to use overall R squared to talk about the amount of variance in the dV that all of the IVs take up. And this is our effect size for the overall equation. And we're going to use PR, or PR squared, to talk about the variance from only one IV over error, so the variance not accounted for. And so this is sort of a measure for each individual predictor, the strength of that, how much variance it's accounting for. So we've got essentially like ANOVA, we've got an overall effect size and an effect size for each predictor, just like we had eta squared and Cohen's d before. So when we do these, there's two questions to answer. Is my overall model significant? Can I predict y? And then which one of those predictors are useful or significant? All right, we're going to use that books attendance example that you'll see again if you watch the moderation lecture. And we're going to look at the number of books a person reads in a course and the number of times they go to a class and use that to predict their final course grade. Now, do they both predict final course grade or does only one of them work? First things first, power. So to calculate power for this particular analysis, we're going to click on F-test. And then linear multiple regression, fixed model, deviation from 0. We could pick the increase one, but that's going to be more for hierarchical regression. And we're using multiple regression because we have more than one predictor. So we're going to click determine and use an R-square effect size that we think might be accurate. So we're going to use a small effect because we don't know in this example. Alpha is 0.05, power is 0.8, and then we fill in the number of variables. So let's click determine here, and from squared multiple correlation, so I use 0.01 in my example, calculate and transfer to main. Alpha is 0.05, tab is not working, right? Power is 0.80, and the number of predictors in this example is only 2, one for books, one for attendance. So it tells me that if the effect size is truly small, I'm going to need nearly 1,000 participants for this particular study, which is probably doable if I'm using maybe a large intro to psych class or across all the classes, but more than likely not doable to keep track of that many participants. So let's pop over to R and work on our assumptions. First one is going to be accuracy. So I'm going to set my working directory and load the data set. Now for accuracy, I just want to make sure that these numbers make sense. So there are no negative books, and there are no negative attendance scores, and no negative grades. Grades don't go over 100, and these numbers are appropriate for the scale of that particular data. Now notice that the scale of the data is different for each one of these, and that'll be important when we start looking at beta as a way to compare which predictor was better. I can also see that I don't have any missing data, so I'm going to skip that step as well. So we're going to essentially pop straight down to outliers. And to do this, we're going to calculate Mahalanobis distance scores. And so this is going to be different. And if you're watching these in order of the classroom materials, this will be the first time that we've done a data screening that involves our 3 different sets of outlier analyses. And so you'll see this again in the hierarchical video and the mediation and moderation if you watch those. So Mahalanobis is going to be kind of business as usual. But what I'm going to have here in the code is that we're going to first run that final model. We don't have to do a fake regression because we're doing real regression. And so we can use our real regression analysis to calculate the numbers we're interested in. So I'm going to run the last model, and in a simultaneous regression, the first model and the last model are the same thing. When we get to hierarchical regression, the first model and the last model are not the same thing. So remember, use LM. DV is predicted by, that's that tilde, IVs. So just add them together. Right? Data equals our master data set because we didn't have any typos. We're going to use that in just a minute. So down here for Mahalanobis, we'll put in all of our variables because we're interested in screening across all 3 of them. So this is the same way we've been doing data screening. Our cutoff score is 1 minus the big important rule. Degrees of freedom is based on the number of columns that we put in. So that's 3 in this example. So that gives us 1627 with 3 degrees of freedom. Now this is going to be a little bit new. What we normally would do is type summary of Mahal less than cutoff. And we would just see how many people were false. So how many people were greater than the cutoff score, which would be bad. Now what we're going to do is reverse that idea so that we can calculate outliers for 3 different screening procedures and then use them all together. So we're going to calculate how many times is Mahalanobis greater than our cutoff score. And what happens when you do that, oops, wrong way, is you get these true falses. So right now, no one is greater than the cutoff score. But what I'm going to do is take those true falses and convert them into numbers. And that's going to make them 0 for false and 1 for true. And we're going to keep a tally of how many times a participant hits on a cutoff score. So how many times were they an outlier? And that's going to be really useful when we're totaling them up. Oops. So our bad Mahal here is just a set of 1s and 0s, where 0 is that they're not an outlier and 1 is that they are an outlier. Now for purposes of my class, and maybe for if you're doing a write-up of this sort of thing, you might use this little table function to look at how many people were Mahalanobis outliers, which in this case is none of them. So there's no 1s here. All right, this text explains all that. The next thing we're going to do is leverage. Leverage is how much influence a person has of the slope. So it's a score of how much the slope changes when you are in the equation versus when you're not in the equation. And you're hoping that that number is small, is that the slope is a good overall estimate of how much x is increasing with y or decreasing. And really with participants who have big numbers here, that means they're changing the slope a lot. So that one person is influencing the slope, which means that they're creating the slope, which you don't want. So what you're going to do is fill in k, and then don't touch a lot of this code. So we'll use leverage equals hat values is the way that leverage is calculated. This output here is from our saved regression equation that we're going to use for all of our data screening. The cutoff score is 2 times k plus 2 divided by n. Leave in those parentheses so that R does the correct order of operations. You should get small positive numbers here. We're going to calculate our cutoff score by calling it cut lev. So cut Mahal, cut lev, or cutoff. Cut cooks here in a second. So the cutoff score for each one is different. And we're going to divide by n row of the data set. So let's see what that looks like. I filled in k as 2 because I have 2 predictors, books and attendance. Calculated my leverage scores. So these are the scores for each participant, how much they changed the slope. That in itself is not super useful. Let's calculate a cutoff score, and it's 0.15. So people are only heavily influencing the slope if they are past 0.15. So we're going to do the same thing here that we did up here by calculating how many times someone is above the cutoff score and giving them a 1 if they are. That means that 2 people here are outside of that leverage criterion. Remember, the numbers across the top here are 0 for not an outlier, 1 for an outlier, and then there are 38 participants who are not an outlier and 2 participants who are. But we're going to throw in one more of here, and that's Cook's. Cook's is a measure of influence and discrepancy, which means that it measures how much they influence the slope as well as how far they are away from the rest of the data. So to get those values, it's Cook's.distance, and that's again on our saved output from our regression that we're using to screen the data. The cutoff score for Cook's is 4 divided by degrees of freedom residual, so n minus k minus 1. And so we'll do 4 divided by n rho for master minus k minus 1. And this is really whatever data set you're currently working with. So it might be no typos. So let's create those. Let's create that. One thing you'll want to do is add Cook's here just so you can see the cutoff score because I will ask you what it is. And again, it's a small positive number. It should also be fairly close to leverage. They're not quite the same. But they're usually pretty close, and that's one way you know you're doing it right. Let's again calculate how many people are bad, and we've got 1 person who's outside the Cook's cutoff score and 39 people who are not. Now what do I do with all the information? Well, I'm going to add all 3 of them together, so add bad Mahal, bad leverage, and bad Cook's together. And what that does is create a total outlier score for each participant. So it's essentially marking how many strikes they got. And this is 2 strikes, you're out. And so anyone who keys or hits or whatever battleship example you want to use here on at least 2 of them is going to be considered an outlier. So I'm going to make a table here. And I can see that I have 3 people that had either Cook's or leverage. But nobody who has 2 or more. So we would be looking for anybody who has 2 or 3, because you can actually be an outlier on 3 of them. And so in this particular example, we have no outliers. However, we can keep using the code and provided here, and this will subset that data set where our total number of outliers is less than 2. Now remember, this master data set may be no typos if you had to fix accuracy. But we want to exclude anyone who has 2 or more outliers. That's nobody in our particular example, so our master data set and our no out data set are the same thing, but that's okay to have it saved twice. After you exclude people, you want to get into your regular assumptions checks, so we're going to start with additivity like we always do. However, if you actually excluded people, you want to make sure you rerun that regression, because you don't want to base your assumptions checks on data sets with outliers in it. And so we'll just rerun that exact same regression output from earlier, but now we're going to call this, change the name of the data set from master to no out. You'll notice that I'm still not running a summary here because I'm not interested in the output just yet. I want to make sure my assumptions still match. Here, we don't want our IVs to be too correlated. Now we want it to be correlated with the DV. That's the point. So here I'm just really interested in the IV correlation. Anything over 0.7 starts to run the risk of suppression, and anything over 0.9 is multicollinearity. So we just want to make sure we don't have any of that going on. Oops. So I can run my correlations like I normally do for data screening. And I just want to look at books and attendance. They're correlated at 0.4. So that's okay. I can also use my symbols for numbers table. And additionally, there's one more option to run a summary of that output from up here, this one, and say correlation equals true. And that's actually going to give you a correlation here of just your IVs. So you can't accidentally tell me that the IV and the DV are too correlated. And what you want to do is ignore the intercept component and just look here at books versus to attendance, and you'll see that that correlation is 0.44 like we found a minute ago. That's just one more option. All right, let's scroll through all this stuff. So this is basically don't tell me about the IVs and DVs being too correlated. And now we're going to run the rest of our assumptions. We've already run our regression, no fake one necessary. So we're going to run the standardized residuals or studentized residuals. And then calculate our fitted scores. So we've got our error and our estimate of how well you did. And we're going to z-score the fitted scores to make interpretation easier. Let's walk through our assumptions. So this is not random, so we should all get the same pictures. And this looks pretty good. It's centered over 0 between 2 and 2. It's a little uniform, but it's all right. Our linearity is really good. Now for homogeneity and homoscedasticity, let's start with homogeneity. It's pretty good. This is probably 2 like out here. So it's pretty much 2 to 2 this way, and it's pretty much 2 to 2 this way. Nice even spread. For homoscedasticity, I would say this is just a bunch of blobby dots. Okay, maybe some holes here and here, but generally pretty even spread across X here. So that looks pretty good. The more participants you have, the better these become, and also more power, more stable estimates, etc. So to get into the actual analysis, you'll notice that there are like 80 lines of code to screen the data, and then the actual analysis itself is 2 lines of code. So I think that's the way it kind of always seems to go, is that the setup takes longer than the actual analysis. But what we're going to do is run that regression for real this time. And it's going to look the same as the way we data screened it, but I'm going to call it model, just so I know this is the one I'm really interested in, and it's not part of my data screening. And run a summary of that model. Okay. And that'll be useful if you kind of follow that pattern to keep yourself straight on what you're doing. Also, it'll be useful when we get into hierarchical regression, because then we'll have model 1, model 2, model 3. Right, so I run it. Now I'm going to look at a summary. So I'm going to come over here and explain to you what's happening in this summary. Go away. I don't know why my taskbar won't go away. There we go. The first question we're going to ask is the model significant? And all that magic happens down here at the bottom. So my F statistic here of 2 and 37, so 2 and 37, is 906, 906. P is 0.0006, so less than 0.001. R squared here is under multiple R squared. So yes, the overall model is significant. We can predict grades with books and attendance, and it's a fairly large effect size. Are the individual predictors significant? Yes. So books here is at 4 points. The standard error is the next line. Here's T, and here's P. So we would say B equals 404. T 37, where this 37 came from, is the second number here. And these should be in italics. 2.30, P equals 0.03. Attendance is also significant. T 37, pulled from the second degree of freedom, 2.19, 0.04. How do we interpret these numbers, though? And it's as the number of books a person reads increases, because it's a positive predictor, so does grade. I can be even more specific than that. For each book I read, I get 4 points on my final grade. That's a lot, so you should be reading the books. But there aren't books for this class, so you should be reading the notes. For every class I go to, I get 1.28 points on my final grade. So an easy way to raise my grade, a half a letter grade, is to read one of the books and go to at least one class. Now, if these were negative, what you would do is say, for every increase, I get a decrease in Y. Those are, as one goes up, the other goes down. However, at the moment, I really can't compare these two. Because they're on different scales, because the books is 0 to 4, attendance is 0 to 20. So quantsci is a great package that has a beta function. You could also z-score the variables first, but I find this to be just as easy. So we're going to load the quant sci library. And then the function is lm.beta on our model. So the model here. This will not run on categorical predictors, unfortunately. And so now these are the beta values for our original Thor and 1. Now we can see how close they are. So even though 1 and 4 seem like very different numbers, when you z-score those, they're approximately the same weight. So books is winning just slightly. It's a slightly better predictor. But I would say not by much, and certainly not by any significant amount. To get the partial values to have an effect size for each of these individual predictors, we're going to use PR squared. PR squared can be obtained from the PP core library, and the function is pcore for partial correlations. So PP core stands for part and partials, and P stands for partial here. So load that bad boy. We're going to save these as partials and use the pcore function. You put in the name of the data set minus any categorical predictors, and we're going to say method equals Pearson, so we get Pearson's PR. And all that is, when I look at it, it's just the partial correlations. However, it's very tempting to just look at these numbers and type them in blindly. But you have to remember that we want PR squared. So I put in a little piece of code here that takes those R values and squares them. Estimate here is the correlation. P-value is if whether or not that correlation is significant. Statistic is the T-value associated with that. Not so interested in those, just want to get PR squared here. So now I'm going to look at grade. Books for grade is 13% of the unaccounted for variance. Attendance for grade is 11% of the unaccounted for variance. So just like beta, this will kind of match where if one beta is much bigger than the other, usually the PRs will be much bigger than the other. But this is unaccounted for variance. So don't expect this to add up to R squared. In our particular case, this adds up to what? We got 13 and 11, 24. Remember, R squared was 33. R squared and PR squared have different denominators. So you should go back and watch the overall lecture video. And you know that our PRs cannot add up to R. I mean, they can. PRs don't tend to add up to R squared. Sometimes they add up to more than R squared because the denominators are different. Now, making a plot. So we're going to make a graph, and this is kind of the ultimate goal here, of our predicted score. So this is our score we would expect someone to get. So I wrote books plus attendance because that was my regression equation. And then our actual score, and see how well we did. We can't make a single scatter plot because we have more than one variable. And making a multi-way scatter plot can be very confusing. So I don't know if I would publish these, but I find them very helpful. So I just ran open ggplot2 and I ran my cleanup code to make this graph look nice. I can get my final fitted values. This is y-hat. This is our predicted score. That's actually very similar to what we do when we do data screening, except now we don't want to z-score them. So our fitted scores, in this particular example, is just a score I would have predicted you to make in the class. We're going to make a scatter plot of our, on our no out data set. We're going to pull those fitted scores and plot them against the actual score, which is grade. Take that scatter plot, clean it up, add some dots. Here we're going to add a line and a smooth line, so a straight line, and make it black. And then I added some X and Y labels for clarity. And what that does is it creates a regression, creates the regression line that we would have used to predict. Now I don't have each one separately on here, but I can see how well I'm doing. So how close is each dot to the line? Because if I predicted you make a 50 and you actually made a 30, I'm a little off, right? So we would want your predicted scores to be very good. And it also give you a confidence range on those predicted scores. So this just allows me to kind of see how well am I doing. Here's my predicted score and here's your actual score. I'm doing okay. Because there are a lot of influences on grade other than books and going to class, like studying. So when you go to write one of these up, what you'll do is talk about data screening first. Then you'll talk about the overall model, which has a weird little F here stuck in there. All right, and then you'll want to talk about each predictor separately. Here I included beta. You don't have to include beta. You could do B. In this example, maybe I wanted to compare B and beta. Toss some zeros in the front there. And then it says C figure 1 for representation. So you can do B or beta, just be consistent. And all of that together is a simple multiple linear regression doing simultaneous entry and examples on how to write that up.